Welcome to another of my mind-bending videos on using Microsoft Excel. In this example, we want to use the GoalSeek and Solver features of Microsoft Excel to find the values of the friction factor that are given by the Colebrook relation. I think I can find a way to represent that for you. Yes, I think we can insert an equation here using this equation editor. Um, the Colebrook relation is an implicit relationship for the friction factor F. And the way you see it written in Hodge and Taylor in page 9, equation 1-14, is something like the following. It's given as this implicit relationship that shows the square root of f on both sides of this equation. And since the square root of f is on both sides of the equation, it's not possible to solve for the friction factor explicitly. We can't find a way to isolate square root of f. So we need some kind of iterative solver, root finder, if you will, thinking back to your numerical analysis class. But in Microsoft Excel, there are two features that can be used to do this. One is called GoalSeek. They are both standard features of Excel, but GoalSeek is always available. The solver feature, on the other hand, must be enabled if it has not been enabled on your Microsoft Excel version. But nonetheless, it is supplied with the software. So to begin with, let's just explore how we can use the GoalSeek function to find the value of the friction factor for given values of the Reynolds number and this relative roughness. The epsilon divided by the diameter is the relative roughness. I'm just going to call that E over D. So if we assume that we've got some known Reynolds number, maybe 100,000, that's kind of in the middle of the range, and E over D, which could be, I mean, you could find that. Yeah, let's say instead that it's equal to commercial steel pipe, which has a absolute roughness of 0.00015, and that the pipe diameter is maybe 3 inches. So that would give us a relative roughness of 0.006. So for that combination, we want to find the value of f that satisfies the equation that you see there. So to do that, we're going to set up, let me set up two cells. One cell has the value of the unknown f, I'm calling that f Colebrook, and then the other has something that I hope will be equal to 0 once f Colebrook is known, and that's going to be this equation, or a rearrangement of this equation so that when f is known, the result of the equation is 0. So in other words, I'm going to maybe rearrange that equation a little bit. And let's write it as, I'm going to use the power of exponents here. To be explicit, I'll write it this way. Yeah, so see, I'm going to, since it's a logarithm of something raised to an exponent, it's the same as that exponent times the logarithm of that thing. So I'm going to use that property of logarithm, and then I'm also going to say, well, this is actually just the sum of these two things. So I can simplify this a little bit and write it this way. So what I'm actually going to do is I'm going to call this quantity 0, and when I search for the value of f, when I find the correct one, then it should be equal to 0. So to do that, I'm going to make use of these named ranges that we've used before. I'm going to highlight the names in the left column and the values that they will be identified with in the right column. And then I'll go to Formulas, Create from Selection. And by choosing Create from Selection, then Excel examines the selection and suggests that there are some names in the left column, and in fact that is correct. So I'll just say OK. So now I should have some names that I can use to refer to these numbers. The Colebrook has no value right now, F Colebrook, but let's put in a number for it. The friction factors can range from, if you look at your Moody diagram, practically speaking, they can range from 0.01 all the way up to 0.08. So there's not a huge range, but they're on the order of 10 to the minus 2. So I'm just going to put in 0.01, which would be a pretty low friction factor. And then I'm going to type in that formula that you see up above. So this is equal to 1 over the square root of F Colebrook plus 2 times the logarithm of E over D divided by 3.7 plus 2.51 divided by the quantity RED times the square root of F Colebrook. So I think that closes out all the parens, and if we had the correct value of F Colebrook, this should be equal to 0. And we can see that we don't have the correct value of F Colebrook. And so since it's the incorrect value, we have something different from 0 here. So now we can use the GoalSeek function, which you'll find on the Data tab, and it's under the What If Analysis section. And if you bring that up, you can see that GoalSeek is one of the functions that's here. What GoalSeek will do is it will find a single value, a single cell, really, find the value in a single cell that causes a target cell to be a known value or a specified value. In this case, our target cell is the one labeled 0, and the value that we want it to take on is in fact the value of 0. You'll see when I bring up this dialog box that I choose which cell I want to set, and by default the one that was highlighted when I invoked the GoalSeek function is the one that is selected, and in fact that is incorrect. I want to set the cell called 0, which is B14, equal to a value of 0, and I want to do that by changing the cell called F Colebrook, which is B13. I'm not sure. I think we can put names in these boxes for the GoalSeek. I know you can on the solver, and we'll see that momentarily. But for now, I'm just going to point at those cells and select them. So once I choose, I want to set the cell called B14, 0, equal to a value of 0 by changing the cell F Colebrook, which is B13. So when I say OK, Excel goes about its business trying to vary the values in Colebrook, F Colebrook, to try to make this equal to 0. And after just a little while, Excel comes back and says, well, you wanted 0, but I have 0.0009. Is that okay? And we can say that's okay. You might try to see if Excel can work a little harder and improve that answer by going to your what if analysis and running the GoalSeek a second time. I'm not sure that we'll get any improvement here, but we can try it. It's working. It says it found a solution. It didn't change the value. So that seems to be as good as it can do, but you see the 0.0207 is the value. So that's how we can do that using the GoalSeek function. We could also do this with the solver feature. I'm going to rename this GoalSeek. And then if we copy this over to another sheet, I'm going to show you how we could do exactly the same thing using the solver feature. Now, unfortunately, the way I have the screen set up here, the solver feature is just a little out of view. It's off to the right here. But first I need to show you how to activate that. I like to have this developer tab showing on my Excel screen, and it won't be shown by default, but if you do have the developer tab, you can get to these add-ins pretty quickly and enable them. I'll just show you how to enable that developer tab. If you go to the File section of Excel and choose Options, on the Customize Ribbon option, the only thing that's not checked, if you go over here, is this Developer tab. I'm not sure why it's not active by default. Apparently there's possibility that some people are confused by this, but if you just say on the ribbon, please show the Developer tab, then when you do that, then this Developer tab will be present, and when you go to the Developer tab, you can go right here to where it says Excel add-ins, and that's going to allow you to easily check that you want to use the solver add-in, which is one of the default add-ins. Some of these add-ins that you see here are not standard, but the solver add-in is a standard one, and if you just check that you want to use solver and say OK, then when you go to this data tab, go back to the data tab, you'll see the solver option in the far right end of this window. It's in a little section that says analyze, and the only thing I see in there on mine is the solver add-in. So once you have that solver add-in available, you can use it to minimize a function, or maybe set a function equal to a certain value. I tend to use it to minimize a function, and the reason for that will be a little more clear when we talk about maybe doing this for a number of these all at once. But just for now, let's consider exactly the same problem, that we want to find the value of f that causes this equation to be satisfied. In order to do that, let me go back and pretend that I didn't know the answer, and I guess I put in 0.01 for my F Colebrook value. And I want to change this function just a little bit. Instead of working directly with this sum of these two parts, this left side of this equation, I want to take the whole thing and just put parentheses around the whole thing and then square it. In other words, we're just going to take the square of that value. So the reason I'm doing that is that makes this now a purely quadratic function from a mathematical point of view. And when you think quadratic function, think of a parabola. Because now what we're going to do is use the solver feature to drive the solution down the outside of that parabola to the minimum point. And the reason to do that is the machinery that's inside solver is really, that's what it's trying to do, is minimize something. And by making this a parabolic shape or a quadratic shape, it makes it a lot easier for the Excel solver to do what it's trying to do. Okay, so all I did was I took the left side of this equation that we already had coded, and I put parentheses around it and added the square to it. And again, I apologize, the way my screen is set up, you can't see that. It's cut off a little bit on the right over there. But I guess I could scroll across and maybe show it to you. Yeah, so there you see, there's the equation that I have in that cell, and I just added the parentheses around it and put the square there. Well, regardless, you see that what I had there before was about 3 point something, and when it's squared now it says it's 10 point something. Big deal. Well, if we go to use the solver function, we now will, let me choose this F. Colebrook cell, and I'll go up here on my data tab, and I'm going to choose solver, which, as I said, is just beyond your vision off here to the right. But when I click on solver, it brings up this dialog box. And so it wants to know, what is it that I'm going to operate on? And let me explain now what solver does. Solver can minimize a function, as I said, but it can be a function of several variables, not just a single variable. In this case that we're looking at right now, in fact, there's just a single variable F. Colebrook that we're looking for. But this power can be exploited in to solve for a number of these all at once, and I'll show that next. But the difference between solver and GoalSeek, GoalSeek can only consider a single variable, X, let's say. GoalSeek can only consider a single variable, but solver can work with a number of variables. Both of them can only operate on a single function. There's just a single result that depends on one or more variables. So solver can handle multiple variables. GoalSeek can only handle one variable. Okay, so back to this story. We can use the absolute reference $13. We could also type in there that what we want to minimize is the cell known as 0, but we want to minimize, not maximize it, and we're going to do that by changing the variables known as F. Colebrook. Okay, now you can add constraints as well, so it minimizes in unconstrained, or we could add constraints. We don't really have any constraints. You'll note that there is a default option here that says to make unconstrained variables non-negative. What does that mean? Unconstrained variables. Well, we don't have any constraints, and so it means any variables that are not constrained will be restricted to positive values. And so what are our variables? F. Colebrook. And it's true that we don't want to consider any negative values of F. Colebrook. So this is correct. We want to leave that checked. It's not always the case that we want to consider only positive values, but in this case, it is true. We only want to consider positive values. So yeah, let's wind it up and see what happens. I'll hit the solve button and see where it goes. So pretty quickly, Colebrook came back sorry, Excel came back with the values. It says, look, you wanted 0. I've got you wanted this minimized. I've got something times 10 to the minus 25, and here's the value of this variable that you wanted to know. So do I want to keep the solution? I say that's done a pretty good job. Yeah, that we wanted this to be minimized, close to 0, and it's something 6 times 10 to the minus 25. It's pretty close to 0. So just to compare with GoalSeek, and let's rename this. Oh gosh, I guess let me do this. I'm sorry, we've gone off somewhere. There we are. So now we're back. I wanted to rename this and make this equal to solver number 1. And I was going to compare this number to 6 decimal places, 020727, 020721. So, I mean, I don't think you can probably believe more than 3 or 4 significant figures in this result. But my point here is that the solver is able to get much closer to the correct value that satisfies this equation than the GoalSeek could. Now, with that said, I need to look at this and let you know I probably changed some of the options on this. I didn't intend that I had done this, but I think I did it earlier and it's still here. So let's go and look in here. If we go to the solver feature and bring up this dialog box, there's a section down here that says options. And so if we go to the options, and I have to drag it across to show it to you. Yeah, so it's true. It looks like, well, no, this doesn't seem to be changed. These look like the default values, but I typically will change these. I'll show you on the next screen, but it looks like these are with the default values, which I recognize, and so it looks like it did a fine job. It was an easy function to drive that all the way to 0. All right, there's one last thing I want to show you about this solver, and that is the ability to exploit the feature that it can deal with a single function that depends on multiple variables to find many values, solution to many variations of that equation all at once. What do I mean? Well, suppose we wanted to find the value of the friction factor for many Reynolds numbers all at once, several of them. Maybe we want to make a graph. So if we wanted to create something like the Moody diagram for a number of different values of the Reynolds number, let me clean up these comments in here, which I can't do at the same time I'm talking to you, but I'm going to say that the second tab is using solver. Okay. And maybe probably should put some comments in here since it's not obvious what we did. But we can come back and clean that up. But what I want to do on this sheet is to use solver to find F for many given values of RED and one value of epsilon over D. So what we're going to do is reconstruct this. I'm going to use this same, well, not quite the same formula, but let's say this is our 0 column. We want these to be equal to 0. And we want these to be our values of the function that we're looking for. And our Reynolds numbers will be over here. And let's just say that we wanted, this is going to cause some grief here. There you go. and we're going to fix it here in a minute. We want the maybe plot the value of a Reynolds number from maybe to transition Reynolds number, maybe up to maybe 1,000,000. I don't know. Maybe we want to do quite a few of these, and I'm going to do it sort of in what is this, a logarithmic fashion, I guess. I'm going by 10,000s. Now I'm going to go by 100,000s until I get up to 1,000,000. So there we go. So all of these cells, I'm going to redefine Reynolds number, Colebrook, and 0. I'm going to redefine all of those using the name manager. So I've highlighted now the whole column of Reynolds numbers, the whole column of Colebrook, and the whole column of 0. And I'm going to create from selection using those columns. And so now Excel says, looks like there are names in the top row, and in fact that's correct. So I'm going to say okay, and he says, do you want me to replace this? Yes. Do you want me to replace this? Yes. Yes. So replace all those names. So now those names have a new definition, and I'm going to now do something that seems a little bit odd. Is I'm going to take that square that I put on that formula. I'm going to take that square off of there, and so now this, yes, this is the formula text of what's in there, and you can't quite see, so I'll scroll it across. That it's saying that this is equal to 1 over the square root of f Colebrook times plus 2 times log of this, and blah blah blah. So I took the square off of it now, and the reason for that will be clear, I think, in a moment. But so the value that we had for Colebrook, again, I don't know what the number is. Maybe we'll put something kind of in the middle of the range here. But let me copy these formulas all the way down. Oops, I want this actually to be the same number all the way down, because I want some realistic numbers in there, or at least ballpark numbers. That's important because of the way that the solver feature works. It just takes what it has as a starting point and tries to improve the answer from there. And if you start out too far away from the answer, it can't get there. Okay, but anyway, this is the formula that's in this cell, and it's in all the formulas down below. I'll repeat something that I've said before in case you haven't heard it. Recall now that, let me look at this formula in highlighted Excel fashion. He says F Colebrook, and he's showing me that that's a column of all these numbers. The whole column is highlighted blue. And E over D, that's just this single value. That's good. But Reynolds number is also a whole column of numbers. When Excel encounters that in a formula like this, he says, well, square root is supposed to be just a single number, but F Colebrook is a whole vector or array of numbers. Probably what is intended is that I should just use the value of F Colebrook that's on the same row that this formula is on. So Excel just does that very quietly, but that's exactly what we intend here. We want it to just use the value of F Colebrook that's on this line to evaluate this cell. Okay, so C13 is only using the value of B13 and A13, even though the formula says F Colebrook, which is a whole array, and RED, which is also a whole array. All right, well, anyway, that's the setup. One last thing we need to do, I'm just going to come over here and do it. I'm going to make another cell. It can have any name that you want, but I want to create something called the sum of squares. There's an Excel function that's called sum of the squares, and so if I give it an array, such as the array called 0, and tell it I want the sum of the squares, it's going to do what that name says. It's going to take the square of the first value plus the square of the second value plus the square of the third value and so forth for all of those entries in that array, the array known as 0. So, and what we want Solver to help us do now is to minimize that thing that's actually equal to, let's see, I can show it to you, formula text of that thing. We can either use a name for this or not, but I'll make a name called minimize. So now we want to go to the, so what is this? This is the sum of the squares of the differences, discrepancies, or errors, whichever term you like to apply to this, that result from having the wrong value of the Colebrook friction factor in this Colebrook expression. So I've squared all of these numbers and added them up, and that's what is in this cell over here. So now I want to get Solver to help us by setting the objective function called minimize, and we want to minimize it, and we want to do that by changing the cells known as F Colebrook. Now remember, now F Colebrook refers to an entire array or vector of those values. And so when I use that name, Excel understands it as such, and it's going to manipulate all of those values. I still do want this default constraint that makes these non-negative. So we'll leave it checked. We'll come back and look at those options that I talked about a minute ago, but for now, let's just see what happens when we try to solve this. So I'm going to hit the solve, and it says, hey, it looks like I've got a solution. You wanted to minimize that thing, and I came up with 4.7 times 10 to the minus 5. How's that? And you say, well, that's pretty good. I'm going to do something a little counterintuitive, and that is to just repeat the process and see what happens. So we came up with some ballpark guesses. We asked for Solver to improve those, and now we're going to ask to see if it can improve it any further. And it looks like at this point it says, look, 4.7 e to the minus 5 is the smallest value I can get right now. How about that? So that's pretty good, but you got to understand these numbers in the cells over here are supposed to be equal to 0, and they're not. Yeah, I'm getting a little background action on this other file. Let me just close this other file. I think we're through with it. Yeah, throw that away. So here we go. Yeah, these are supposed to be 0, but they're 10 to the minus 3, and that's pretty close to 0, but we really want all of these to be really small. So if we go back into the solver and look at those options that I talked about a minute ago, there are two options in there that I think you should change. And one is, so they're both on this tab that says GRG nonlinear. What that means is generalized reduced gradient. That's the nonlinear solver mechanism or algorithm that Solver is using to minimize this. In order to use this gradient method, it needs to approximate the derivatives of the function. And the default is to do that with a forward difference model. If you've had a numerical analysis course, you should remember that there's something else called central differences, and that central differences are a little more accurate than forward differences, but they also are a little more computationally expensive. But we don't really care because this is so easy to solve. So using central differences will help. Another thing is this default convergence. I usually like to add a couple of zeros in there, which means that Excel has to work a little harder before it gets tired and says, hey, I think I've got an answer for you. So change this to central differences and add a couple of extra zeros to this convergence tolerance, and then try again. So now with exactly the same setup, let's just see if the solver will do any better. So now it does come back and say, okay, I think I have an answer, but you'll notice that this minimized cell, the sum of the squares, is equal to something 10 to the minus 14. And these ones that are in the 0 column are now on the order of 10 to the minus 8th, 10 to the minus 10th. So it's much better. And sometimes, again, if you just try to encourage Excel to work a little harder, sometimes it will, sometimes it won't. But here, I'm not getting any smaller than 1.95 times 10 to the minus 14 for the objective function, but these 0 values are much, much smaller. Again, Excel has spit out all these decimal places for these Colebrook function friction factors. I don't think you can really believe all those, but probably you could easily take 4 figures on this as being true, certainly 3 of them. But I think you could, with this kind of satisfaction in the function, I think you could say that these are probably accurate to 3 to 4 significant figures. Okay, so to summarize, we use the GoalSeek function that's native in Excel to find the root or value of f for the Colebrook function that causes it to be satisfied. We also talked about using the solver function to do the same thing when we just have a single unknown variable, f, to minimize the square of this function and drive this down to 0. And we got a really good value for one value of the Reynolds number and one value of the epsilon over d. We further looked at the the solver feature, and took advantage of the fact that it can actually work with a number of variables. Looks like we had about 20 of them in this array called F Colebrook, and that we could minimize the sum of the squares of many of these equations, 20 of them approximately, simultaneously by using that solver feature. Okay, I hope this will help you understand how to use these two built-in features of Excel to help solve algebraic equations.